Hey everybody, Mr. Klein here, in a hat. It's fun. We're on the second page of the limits document, and here I want to talk about some things that we already know about functions. So suppose we're interested in what happens as x goes to infinity, and I ask you about this function right here. I expect that you will know immediately where this is going, and there's two ways that you could figure it out. One is you could plug in a big number. I'm going to say a big number is 10 in this case. 2 to the 10th power is 1024, which is big. So that suggests that y is going to infinity. Also, we should know from all those years that we spent studying exponential functions that this graph looks like this. So you can see that y is headed up to infinity. So in this case, we'll have what we call an infinite y value as x goes to infinity. In contrast, suppose we're looking at a function like this. Well, if I plugged in a big number for a half, and I'm going to pick kind of a lame big number again, I'm going to do 1/2 to the 10th. That would be 1 over 1000 to the 24th, which is pretty darn close to 0. Also, we know that because the base is less than 1, this is a decay function, and decay functions hug the y-axis as x goes to infinity over here. So this would be a function where y is going to 0. All right, so with that in mind, here are 3 options for what can happen as x goes to infinity. Y can go to infinity, y can go to 0, or there can be no limit at all at infinity. So I'm going to add that I know y equals 2 to the x goes here. Do this in pencil, by the way. Y goes to 0, goes here. And I'm going to ask you to add some functions to these lists. And those functions look like this. So at the bottom of the page right here, we've got a whole host of functions. And I would like you on your paper on this document right here to take these functions and sort them into the right groups. Some of them y goes to infinity as x goes to infinity. Some of them y goes to 0 as x goes to infinity. Some of them have no limit at all as x goes to infinity. Pause your video right now, and then in a minute you can check. So check your work. Your answers should look something like this. These go to infinity. These go to 0. The trig functions, because they just bob up and down, they don't have a limit as they go to infinity. Now, let's add a couple of these to the paper here. So y equals sine of x, y equals cosine of x. Both of those go like this, right? So there's no value that they're approaching. Now, y equals tangent of x, sometimes I have students say to me, well, I thought that that right there was going to infinity because it zips up to infinity this way. Well, that's true, but that's actually at an asymptote. It's at x equals pi over 2. And it's just going to repeat that over and over again forever. So it's never going to approach any particular number as x moves in this direction. Okay? Now, I'm going to ask you to do a little more work. I would like you to take the things that are on this list right here, and I would like you to put them in order from least to greatest. And here's what I mean by that. Let's take, for example, y equals x squared and y equals 2 to the x. Which one of them is getting to infinity faster? Well, we can actually play around with that a little bit. Let's take y equals x squared and y equals 2 to the x. We both know that these are shooting up to infinity because the parabola, whoop, infinity, and the exponential to infinity. If we wanted to know which one is getting faster, we could just plug a big number in, right? So again, let's try 10. If I plug in 10, this would be 10 squared equals 100. And over here, if I plugged in 10, I would get 1024. So see how the 2 to the x is growing faster, or it's getting to infinity faster than the x squared. So right now, pause the video, and I want you to see if you can put these in order. So here's our results, and let's summarize these. If you're looking at those things that go to infinity, those that get to infinity the fastest will be those that are exponential with a base that is larger than 1. And obviously, as the base gets bigger, it goes faster. The second group right here, I would call these power functions, because they can all be written as x to a power. And the power has to be greater than 0. So we'll say n, the exponent, is larger than 0. And then the slowest will be the logs, which they get to infinity, but they like the tortoise. They take their time. Over here, the exponentials with a base that is between 1 and 0, they'll get to 0 quickly. And then this one right here is also a power function, but it's a power function with a negative exponent. So powers with an exponent less than 0, they go to 0. All right, now, why are we doing this? We're doing this because it's going to help us solve these fraction problems. What we were just doing for the last 5 minutes, that's set up for what's going to happen now. All right, so let me give you an example. Look at the first one. It says, take the limit as x goes to infinity of x plus 4 over x squared. Here's how I want you to approach a problem like this. You're going to say, x plus 4, where does that go as x goes to infinity? Oh, well, that goes to infinity. It gets big, right? It's a line. Goes up. X squared, what happens to that as x goes to infinity? Whoop. Okay, well, that's also going to infinity. Next question, which one's getting there faster? The numerator, which is linear, or the denominator, which is quadratic? Answer, the denominator. So if the bottom is getting to infinity faster, then you are taking something that is relatively small, dividing it by something that is big, and what you are left with is something that is approaching 0. You can punch this into your calculator. You'll see it approaches 0. Let's do another one. Second one, we say numerator. 2 to the x is exponential growth. So that's going to infinity. Denominator is a cubic function. They also go to infinity. So it's infinity over infinity. Which one gets there faster? Well, in this case, the exponential grows faster, right? The exponentials get there before the power functions do. So the top is growing faster. If the top is growing faster, then this function will fly on off to infinity. One more, and this is the weird one. We look at the limit as x goes to infinity of the sine function divided by the cubic function. Okay, so this is a little trickier. Look at the numerator. Does the numerator have a limit as you go to infinity? No, it's bing, bom, bim, bom, bim, bom, bim, bom, bim, bom, bim, bom, bouncing back and forth. But the way you want to think of this is that it is bounded. And how is it bounded? Well, what's the smallest that the sine of x can ever be? -1. What's the biggest that sine of x can ever be? Bing, bong, bing, bong, bing, bong, bing, bong. Well, the largest it ever gets is 1. So this is bounded. Look at the denominator. Cubic function is going to infinity. Now, if you think about it this way, what we are doing is we are taking something that is at its absolute largest equal to 1. That's the biggest value it can ever take. And we are dividing it by something that is infinitely large. And if you take 1 and you divide it by something that is infinitely large, then you get something that is very, 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 very small. In other words, 1 divided by something really big is 0. Okay. Try the next one on your own. Answer is that both x and natural log x go to infinity, but x gets there faster. So overall, the top is growing faster. It's going to infinity. Try number 5 on your own. Now, 5 is a little trickier because the numerator is a power function with a degree of 5. And the denominator is a power function also with a degree of 5. So the numerator and the denominator are both going to infinity. You can say that they're kind of going at the same speed, right? If they're both degrees of 5. Remember what we do in this case is we look at the coefficients. So in the numerator, it's 3. In the denominator, it's 1. So our limit as x goes to infinity will be 3 over 1, which is 3. Try number 6 on your own. On number 6, the numerator has a base that is smaller than 1. So as you plug in large values, it goes to 0. Denominator is infinite. 0 divided by infinity will just leave you with 0. Try number 7 on your own. Number 7 is a trick question. Sine and cosine. If you think of what's sine divided by cosine, you just get tangent. Where is tangent going as we go to infinity? Nowhere. So we would say does not exist. Last one, try number 8 on your own. And of course, the cheetah is moving faster than the elephant, which means the numerator is growing faster. So this puppy is headed to infinity. And ladies and gentlemen, that is the game.